Atoms and elements didn't simply pop into existence. They're the outcome of cosmic furnaces and nuclear alchemy that unfolded over billions of years, governed by the tug of war between the strong nuclear force and electric repulsion. This is the puzzle of nucleosynthesis. How did the universe cook up hydrogen, carbon, gold, and every other element? And why stop at uranium instead of forging an endless ladder of ever heavier nuclei? Right after the Big Bang, the universe was a seething hot soup of protons, neutrons, and electrons. As it expanded and cooled, within the first few minutes, those particles combined to form the lightest elements, mostly hydrogen and helium, with trace amounts of lithium and beryllium. Question: why didn't we get heavier atoms right away? Answer: it was simply too hot and too brief. Nuclear reactions needed more time and the right densities to fuse beyond helium. Enter the stars, nature's long-lived fusion reactors. In their cores, hydrogen nuclei fuse into helium, releasing energy that makes stars shine. Once enough helium accumulates, temperatures rise further, allowing helium to fuse into carbon, oxygen, and neon. Over millions of years, massive stars build up shells of progressively heavier elements, forging silicon and sulfur, and finally iron, the most tightly bound nucleus of all. If iron is the fusion endpoint in quiescent stars, how do we get elements heavier than iron, like gold or uranium? The answer lies in cataclysms, supernova explosions, and neutron star mergers. Question: what happens when a star collapses or two neutron stars collide? Answer: enormous fluxes of neutrons bombard seed nuclei, driving rapid neutron captures that push atomic nuclei far up the periodic table in seconds before they beta decay back towards stability. Slower processes in aging stars, the S process, also sprinkle in a gentler flow of neutrons to ladder up element by element. But why does the periodic table end around element 118 instead of climbing forever? It's a balancing act. The strong nuclear force glues protons and neutrons together, while the electromagnetic force makes light-charged protons repel each other. Beyond a certain size, the repulsion overwhelms the glue, and nuclei become too unstable to hold together for more than fractions of a second. Even in laboratories, we've barely managed to create elements past 118 before they fission apart. In the grand tapestry of the cosmos, nucleosynthesis is the story of how simple particles danced into complexity, stopped by the limits of nature's forces. From primordial fusion in the first minutes, to stellar forging over eons, to explosive neutron blitzkriegs in dying stars, each element's birth reflects the universe's unfolding drama and explains why the atoms in your body bear the fingerprints of distant stars. Immediately after the Big Bang, tilde 13.8 billion years ago, the universe was too hot for atoms to form. Particles existed in a plasma state of free quarks, electrons, and photons. As it expanded and cooled, quarks combined into protons and neutrons within the first microseconds. A few minutes later, during Big Bang nucleosynthesis, simple nuclei like hydrogen, helium, and trace amounts of lithium and beryllium formed. However, atoms themselves, with electrons bound to nuclei, could not form until tilde 380,000 years later during recombination, when the universe cooled enough for electrons to be captured. The earliest atoms were thus shaped by thermodynamic constraints of the early universe. About 75% of the baryonic matter in the early universe became hydrogen nuclei, protons, and about 25% formed helium-4. It's like a chaotic firestorm that cools just enough for snowflakes to begin crystallizing. Atoms are the cooled snowflakes of the early cosmic fire. Heavier elements beyond hydrogen and helium were not created in the Big Bang, but inside stars via stellar nucleosynthesis. In the cores of stars, hydrogen fuses into helium through processes like the proton-proton chain and CNO cycle. As stars age and their cores heat, they fuse helium into carbon, oxygen, and even heavier elements up to iron. The mass and temperature of a star determine how far it can go on the periodic table. Elements heavier than iron require different conditions to form, because fusion beyond iron consumes energy rather than releasing it. In massive stars, elements up to iron are built up in concentric burning shells, like layers of an onion, before supernova collapse. It's like a stellar kiln that forges heavier metals by layering heat and pressure, until it reaches a limit beyond which the process reverses. Elements heavier than iron are primarily formed during cataclysmic events, such as supernova explosions and neutron star mergers. These environments provide the extreme energy, pressure, and neutron flux required for rapid neutron capture and slow neutron capture, nucleosynthesis. Our process can build nuclei with many neutrons in seconds, creating gold, uranium, and other heavy elements. These explosive events also disperse the products of nucleosynthesis into space, seeding future stars and planets. Without these rare events, the periodic table would stop at iron. The 2017 detection of a neutron star merging at GW17880 confirmed that it produced significant amounts of gold and platinum. It's like a cosmic forge that lights up briefly, melts neutron-rich ingredients, and scatters precious metal dust across the universe. Not every possible combination of protons and neutrons results in a stable atomic nucleus. Stability depends on the balance between the strong nuclear force, which binds protons and neutrons together, and the electromagnetic repulsion between positively charged protons. This interplay defines the valley of stability, where known stable and semi-stable isotopes reside. Beyond certain proton numbers, Z greater than 118, nuclei become extremely unstable and decay in milliseconds or less. This defines a natural cutoff to the periodic table, not by principle, but by physical stability. Element 118, oganesson, is the heaviest known element, but its most stable isotope decays in less than a millisecond. It's like building towers from magnetic balls. Make them too tall, and they fall apart before you can admire them. Electron orbitals are defined by quantum mechanics, with discrete energy levels, shells, determined by the nucleus's charge. As nuclear charge, Z, increases, electrons are pulled more tightly to the nucleus, but also repelled by inner electrons, leading to complex orbital structures. There's no hard, theoretical upper limit to atomic number, but at some point the inner electrons may reach relativistic speeds near the speed of light, destabilizing the atom. Furthermore, electron capture and decay processes intensify in superheavy atoms, making them incredibly short-lived. Practical chemistry becomes meaningless past a certain point, even if the atom can exist briefly. Theoretical element 137 is often considered a potential limit because its 1s electron would orbit at relativistic speed, breaking Dirac's equations. It's like adding too many gears to a machine. Eventually, the parts spin so fast, the system breaks down from within. Electrons and protons are fundamental particles with fixed charge and mass, quantized in nature. This discreteness arises from quantum field theory. Electrons are excitations of the electron field, while protons are made of three quarks confined by the strong force. There is no continuum of charges or fractional electrons that exist freely in nature. The universe is built from a limited palette of such fundamental particles, and their interactions determine which atoms are even possible. This fundamental granularity constrains the diversity of possible elements. Quarks carry fractional charges, but no free quark has ever been observed due to color confinement in quantum chromodynamics. It's like Lego bricks. There are only specific shapes and sizes you can use, and no one ever finds half a Lego floating alone. Atomic structure obeys strict quantum mechanical rules, the Pauli exclusion principle, conservation laws, and quantization of angular momentum. These rules define how electrons fill orbitals and how nucleons pack into nuclei. Beyond certain configurations, energy levels overlap or become unstable, causing atoms to rapidly decay. These rules emerge from deeper symmetries of nature, such as gauge symmetries and quantum statistics, that limit what can be built. The periodic table is not arbitrary, but encoded in the fabric of quantum laws. The periodic table's shell structure is governed by quantum numbers derived from Schrödinger's and Dirac's equations. It's like a musical scale that allows only certain notes. Try to play a half note between keys, and it sounds wrong or breaks harmony. In speculative physics, some theories explore the possibility of exotic atoms like muonic atoms, strange matter, or atoms in parallel universes with different physical constants. These would require different fundamental forces or particle masses. If gravity, electromagnetism, or the strong force were slightly altered, atoms as we know them might not exist, or entirely new ones might. But in our universe, the observed constants constrain the diversity of atoms. Infinite combinations are not possible because nature's constants are not tunable locally. In muonic hydrogen, a muon replaces the electron, creating an atom with different energy levels and lifetimes. It's like imagining a world where chess has 200 pieces and new rules. But here, the board is fixed and only certain moves are allowed. Atoms and elements are not infinite in variety because they are limited by laws of physics, quantum mechanics, and the balance of forces. The elements we observe, about 118, are the result of a delicate dance between symmetry, stability, and cosmic history. Nucleosynthesis followed pathways allowed by thermodynamics and nuclear structure, not by arbitrary choice. The emergence of matter is thus both a triumph of predictability and a product of cosmic chance. The mystery is not why atoms appeared, but why these atoms, in this order under these laws, from just 3 particles, protons, neutrons, and electrons, the universe built all known matter via a few billion years of careful assembly. It's like cooking with only salt, flour, and water, yet ending up with a bakery full of different breads, shaped by heat, time, and recipe.